Good afternoon, everyone. A very warm welcome to One Summit. I'm so excited to be here. My name is Madhu. I represent Aviz Networks. Let me reveal the dirty secret of AI. So there is nothing new about artificial intelligence. So it has been there quite a long time. So some of your folks, who are working with HPC networks, they are very familiar with that. They might have deal with InfiniBand or Ethernet networks. So of course, GenAI is at another application, which is actually putting stress on your network. That's what we have business. All of you have a business now. Yeah, I have a full packed agenda. I would like to discuss about what drives this network size and how different are these AI networks. How can we use SONiC to solve these couple of AI problems? I can discuss about, I can walk through various AI use cases. And I can also talk about where are we at the community SONiC. Yeah, so what drives network size? Of course, it is a generative AI. So LLMs or foundation models are hitting the world by storm. If you look at this table, I extract this from one of recent presentations from Meta, which is networking at scale. If you look at the table, these are all large language models or foundation models. It is being trained in Meta. If you look at the row 4, Llama 2, Llama 2 took around, it is a 70 billion parameter model. It's trained around with 2 trillion parameters. It took around 800 zettaFlops of computing power. If you translate into this, it's take around 1.7 million GPU hours per month. Assuming that it is using NVIDIA A100 up to 2K GPUs. If you look at the row 3, one thing is interesting is the same Meta, I think Llama 2 with the 34 billion parameters, they were able to train using production clusters of Rocky. So my key takeaway is Meta should be able to test both their large language models. They get the similar same performance using both InfiniBand and Rocky. So this is the key takeaway I got it from, and this is very good for our SONiC community. And there is a latest Llama 3 with this 7 billion open source model, which is also trained on Rocky V2 clusters. Okay, so having said that, this model is kind of a high compute and high performance network problem. And what changes, so typically changes our network. So typically past a few decades, we have been built various data centers, predominantly server-centric. So the goal is, the basic design of this, the data center design is to connect servers efficiently to support both north-south as well as east-west traffic. Predominantly, we use ECMP to kind of load balance the flows across the fabric. So whereas in the era of AI, GPU became the first-class citizen. It has become a GPU-centric data centers we are building it. And if you look at the picture right, there is a DGX. There are 2 DGX servers interconnected, and each DGX server have 8 GPUs. They are interconnected via NVLink or NVSwitch. Whereas across the GPUs, across the nodes, they are connecting via IP class. So the networks are more or likely we'll be having fat tree-like topologies. We build 3-class or 5-class stage topologies. So ultimately, we cannot we cannot run or we cannot train large language models using a node, right? Ultimately, we have to use a network to kind of put into this network perspective, right? Yeah. So there are I just took this NVIDIA as an example, but the same thing is true with any proprietary technology like XGMI from AMD or any startups which is innovating over there, right? Yeah. So this is what I look at AI networks. The first one predominantly the workload types. So the AI workload types are they are varies from training as well as fine tuning as well as inferencing. The training workloads are more compute and memory intensive, and predominantly to do it in offline or backend networks. Whereas fine tuning networks, which are little less stressful than compared to training. Whereas inferencing is a low latency network where it is front-end network. Basically, it provides real-time inferencing to our prompts or questions. And so as I told you, like this is a massively compute problem, and more nodes are like cluster of nodes trying to solve this problem. So certainly it uses some of collective techniques. In ML or AI world, there is RICL, NICL, this kind of frameworks. They are using various collective techniques to efficiently solve this problem. Of course, like these models are so big, and we need to do optimization like data parallelization or model parallelization and pipeline or tensor parallelization. So these are all, all these three pillars kind of like, defining these AI-oriented networks are different from our traditional data center networks. Yeah, let me take one example. So this is one of the most common collective techniques when they use in ML training. So the name suggests all reduce. So basically, the all reduce operation, combines various gradients from multiple GPUs, and it applies some reduction operations like sum or max or product. And so the results will be distributed across all the GPUs. So this kind of problem kind of is a many-to-one or one-to-many kind of collective mechanism put pressure on the put stress on a network, right? So this is something like in a highway, like all the trucks are trying to get into the same lane, same time, irrespective of the direction. So that's what exactly happening. This is called in-cache congestion. So these many-to-one or one-to-many collective what you see in ML training, they are triggering like in-cache congestions. And if there is a small, is there any link problem, it kind of aggravate this kind of latency. Yeah, these are various collective mechanisms you are using in distributive deep learning, like broadcast, reduce, reduce, scatter, and all together. And okay, so whatever the previous two slides said, they are all like the pattern is something like many-to-one and one-to-many. So whereas these two collective mechanisms like ring all reduce and tree all reduce, these two are very popular in data science community. So the goal is very simple here. So each GPU either send or receive from yet another GPU. So the communication between GPUs is kind of quietly reduced here. Whereas if you look at the tree all reduce, so the aggregations or gradient aggregations will be happening at level by level, like a hierarchical pattern. Like so from the bottom up, the aggregations happen at the from the root, it broadcast all the aggregated gradients, right? So the overall like these two patterns are basically it reduce it alleviates the in-cache congestion. Okay. Yeah. So overall, like this is what I look at as AI networks. The first thing is like the network designs kind of transforming from regular class networks to like fat tree kind of 3 class or 5 class networks. And there are innovations happening like Taurus or Dragonfly kind of various network topologies being discussed. And basically what is needed a high bandwidth, low latency network with Rocky or RDMA kind of quietly supported this. And whereas these are the opportunity we have, what we have. The thing is like, since these, as I told you, like the way the training workloads happen, like many-to-one, one-to-many collectives. So, and the GPUs, the way the tree all reduce and ring all reduce, there is no much randomness over there. So basically, because of there's no much randomness, we cannot use regular ECMP algorithms. We should be able to enhance these ECMP algorithms using some kind of like port pinning kind of stuff, ECMP port pinning or Q-pair port IDs. The second thing is, since these workloads are like bursty or elephant flows, these are high sustained flows, quickly saturating those links. So that's where we cannot build a kind of a oversubscription topologies. So we should be having like a non-blocking, no oversubscription topologies like fat tree as well as like Dragonfly or Taurus. And another interesting thing is like here like all these workloads kind of a drop sensitive or like out of order sensitive, right? So that's why like if a single slow job would have been affected our job completion time of entire workload. So these are some of the opportunities and some of the challenges. So I will in the next slide I mean this is what like so AI fabric, right? So this is what like I would like to use SONiC to solve some of these problems, right? So in order to solve this problem, let's start with leaves, where you can enable Rocky features like PFC and ECN for congestion management as well as traffic controls. And you can apply core routing on a Rocky ports, adaptive routing or cognitive routing, where you can. It also provides some port pinning or like ECMP port selections. And if you have DPUs or like SmartNICs used, you can enable packet reordering at XPU level. This will help to basically take end-to-end congestion control or like packet reordering and assembly. And more importantly, what we need is kind of a proactive congestion management. It is a kind of a telemetry assisted. We wanted to understand the queue and buffer statistics as well as flow level telemetry, which will help us to better load balance the flows across the fabric. Okay, then so far you see we have certain unique characteristics of AI workloads, and we have identified some problems and some opportunities over there. When I say opportunities, in the sense the AI workloads or training workloads are simple and repetitive, so that we should be able to better manage the application. We can do a co-design of application network. So these are a couple of use cases I would like to walk through. So the first one, quite interesting, which is a GPU as a service use case, where the customers are trying to build a factory class topology using a pod architecture. So which is a BGP unnumbered simple IP fabric, where it's completely no oversubscription, one-on-one non-blocking fabric. It is a Tomahawk-based network, and where it uses 64 800 gig switch, 800 gig downlinks, 800 gig uplinks, and 400 gig downlinks, which is connecting to GPUs. So the NICs are supporting around 400 gig, which is TAR2 NIC card. So essentially what customer is trying to do, he's providing a GPU as a service. Both is supporting H100 from NVIDIA as well as MI300 from AMD. Right, so the SONiC is quite fit here, because SONiC is the only one who provides multi-vendor ecosystem. It provides clear choice, control, and cost savings, and also it has the prerequisite features like RDMA, Rocky features, as well as PFC, ECN kind of traffic congestion congestion control protocols. So that's why this SONiC is right fit for this use case. The second use case is the customer is building GenAI fabric for healthcare, where he has H100 superpod kind of compute fabric. So for that, he wanted to go for a SONiC as a multi-vendor network fabric, where he can use BGP IP class as a control plane protocol, and he can make use of RDMA Rocky 2 for high bandwidth, low latency, lossless network. And pretty much SONiC provides container microservice architecture, so that he should be able to better control his deployments. On top of that, he's using his own container management for this monitoring, as well as to orchestrate certain dynamic configurations such as policy management, and he's using once as a Rocky fabric orchestration and monitoring. In addition to that, he's using some AI assistant to kind of to reduce to basically streamline his support operations, as well as to better help his customers. Yeah, the third use case is not a real AI fabric use case. This is a slightly different. It's a Rocky fabric use case. He brought it here, this customer is a surveillance customer, where he capture all the image footprint and store in a storage network. He built a storage as well as a compute network in a rack-to-rack fabric topology. It is very straightforward that he make use of SONiC BGP unnumbered feature and RDMA Rocky V2 feature, and he set up a couple of profiles. So one is lossy profile, one is Rocky lossless profile, another one is Rocky lossy profile. The third one is he set up something like a CNP, congestion notification packet. Whenever the queue kind of overload and you see any packet drops, there is a ECN bit marking is happening. Those markings will be propagated to the endpoints. Endpoints should be able to throttle their traffic. So this is a end-to-end rack-to-rack topology, so which is a completely SONiC-based network using Rocky features. These are the complete, these are a snapshot of the SONiC configuration to set up queue profiles and to enable our ECN for Rocky ports. And so I just showcased that this is a huge configuration. So we need to make sure that this configuration has to go to properly configured on the device. So these are the snapshot how you, so the first snapshot, if you look at the left side, it is clearly showing, so there are no drops on Rocky counters and as well as CNP counters, right? So there is no loss here. So on the right side, it is been set up, how to set up on the servers. I have a quick demo for this. So the goal is we can use SONiC CLI and we can use SONiC commands, but the thing is, since it is a huge configuration, the customer is looking for the buffer template orchestration kind of, can you automate this configuration? And also can you provide a visibility into this configuration, what is happening, like what is configured, what is operational. So that's where I should be able to troubleshoot the network so quickly. Yeah. So overall, like so far I see various opportunities as well as challenges. So this is a slide where I wanted to put out that SONiC is kind of provide all the necessary features to enable these fabrics, and also SONiC is the only one who provides complete control, choice of hardware or multi-vendor, as well as clear control over deployments, as well as ultimately you'll get the TCOs, right? Better TCOs. And also SONiC provides various forms and feeds of hardware from 400 gig to 800 gig. It has a large radix as well as high bandwidth switch platforms. And the essential thing, RDMA Rocky V2 is supported with all the necessary features like PFs and ECN. And there are load balancing algorithms, like in ECMP load balance algorithms, which is essentially provided. And also there are enhancements, enhanced ECMP, where you can add ECMP port pairing into the algorithm. So there are, so I understand there are few gaps to support end-to-end AI fabrics for this ML AI workloads. So that's where there are few enhancements are in the pipeline. Some of the things are already solved in SAI, and these features are slowly we are picking up into the SONiC. We have a work group where we are closely working with that. At Aviz, we are also contributing towards these features to provide better observability as well as monitoring. And the solutions there are two kinds of solutions, like switch-based solutions as well as basically algorithm-based solutions, software-based solutions. Switch-based solutions like schedule fabric or like packet spraying and reordering techniques. Whereas the software-based things like dynamic load balancing, global load balancing, or cognitive routing, or like ARS, adaptive routing features, as well as flowlet-based load balancing. These features are already been solid SAI level, and they're slowly coming, slowly coming into the community. So that's where, like as a group, we are collaborating on it, and we are bringing all these features into the community. So at the end, there is a Ultra Ethernet consortium. It is closely working with the SONiC work group. And it is the goal is very simple. They wanted to build a new transport protocol, which will eventually is going to connect 1 million GPUs across the planet. Right? So having said that, SONiC is prime time ready to kind of enable AI fabrics. And so please join us in AI work group. We should be able to discuss all these kind of use cases. We can better design SONiC for AI fabrics. And so there are various work groups. We can cross-collaborate there. We can bring in best ideas together. So thank you so much for all your contributions. Thank you so much.